Module 1, Lecture B, Values and Variables. By the end of this lecture, you will be able to create variables that store medical measurements, patient labels, and clinical status values. Distinguish Python built-in data types used for numeric, text, and true or false medical information. And use built-in functions to inspect and convert values in simple medical calculations. Medical variables. Variable basics. In Python, variables are labels that store values so you can reuse and manage data clearly. In medical data work, meaningful names help identify information such as patient IDs, heart rates, blood pressure, or age. This makes programs easier to read and forms a basic foundation for handling data in Python. A variable is a label that can point to changing values, such as updated clinical data over time. For example, it can hold a patient's current pain score while earlier scores remain available for comparison. Because variables can change, clear and accurate names are essential to prevent confusion and support safe handling of clinical information. In programming with medical data, clear variable names make code easier to understand and maintain. Names should describe the kind of information they hold, such as a patient label or discharge status, while staying practical, consistent, and readable. They should also avoid exposing sensitive details, supporting safer and more effective data management. Python code, variable basics. Variables give medical values clear names, making health data easier to read and understand. When clinical information changes, reassignment lets those values be updated. The example stores basic patient information using 3 assigned values: a patient label, a heart rate of 88 beats per minute, and a temperature of 37.2 degrees Celsius. This organizes essential data so it can be easily referenced or updated. The patient is marked as currently admitted to the hospital, and their initial pain score is recorded as 6. This gives a simple baseline for tracking changes in the patient's condition over time. The code prints a quick summary of a patient's initial health data. It shows the patient label, the heart rate in beats per minute, and the temperature in Celsius, making the recorded values easy to review. The code displays a brief clinical status update for a patient. It shows whether the patient is currently admitted and reports the initial pain score, giving a quick snapshot of their condition for monitoring and communication. After treatment, the pain score is updated so the patient's record stays current. The updated score is then displayed to confirm the change was stored correctly and reflects the latest clinical information. The process checks the data types of the heart rate, patient label, and admission status variables. For each one, it gets the variable's type, retrieves the type name, and prints it with a short description. This confirms that the variables have the expected types before further processing or debugging. This script shows basic Python variable use through a simple patient example. It stores and prints information such as the patient label, vital signs, admission status, and pain score, then updates the pain score after treatment to demonstrate reassignment. It also uses Python's type checking function to confirm the kinds of data stored in selected variables. Medical measurements. Medical measurements record a patient's condition at a specific moment and are central to clinical computing. In software, they should be stored clearly so they can be displayed, compared, or used later. Giving each measurement a meaningful name links it to its clinical purpose, making the code easier to understand and less confusing. Medical measurements must be stored with the right precision, units, and context. Some values are whole numbers, while others need decimals based on clinical or lab standards. Consistent units, naming, and handling are essential to prevent errors in clinical systems. Medical measurements are essential for tracking health, comparing results over time, and supporting clinical decisions. Values such as blood pressure, height, weight, and oxygen saturation must be stored and interpreted carefully because they can reveal trends, support calculations like body mass index, and guide care. In Python, each measurement should be treated as meaningful clinical data with a clear name, the right numeric form, and accurate real-world interpretation. Python code. Medical measurements. Store clinical measurements in clearly named variables, choose numeric types that match the needed precision, and print concise results so they can be checked quickly. The data records key patient measurements using appropriate numeric values, a heart rate of 82 beats per minute, body temperature of 37.6 degrees Celsius, oxygen saturation of 94%, and weight of 68.5 kilograms. Storing these measurements clearly and with the right precision helps keep the medical data accurate and consistent. To calculate body mass index, first convert the patient's height from inches to meters using the standard conversion factor. Then divide the patient's weight in kilograms by the square of that height in meters. The result estimates body fat based on the patient's height and weight. The program displays key patient measurements and checks the data type of each one. It confirms that heart rate and oxygen saturation are stored as integers, while body temperature and patient weight are stored as floats. This verifies that the values match the expected formats for later use. The output presents the patient's measurements in a clear, concise format. It rounds body mass index to 1 decimal place, shows height in meters to 2 decimal places, displays the calculated BMI, and confirms that the measurements were stored successfully with a true value. This script stores basic patient measurements such as heart rate, temperature, oxygen saturation, weight, and height. It converts height from inches to meters, calculates body mass index using weight and height, and rounds the result for readability. The output shows the stored measurements, their data types, the converted height, and the calculated body mass index, then confirms the data was saved successfully. Clinical status. Clinical status information represents a patient's current condition, care path, or risk level, using categories such as admitted, discharged, or critical, rather than numeric measurements. In Python programs, these values help organize healthcare data for reports, calculations, monitoring, and decision support. They do not replace clinical judgment, but they help software respond appropriately to a patient's situation. When representing clinical status in a program, use labels that are clear, consistent, and easy to process. Choose terms that fit the context, such as positive or negative for lab tests, and high risk or low risk for screenings. Avoid using different wording for the same status, because inconsistent labels can make workflows unreliable. Plan simple, specific values before building your Python workflow. Clinical status values make medical data easier to interpret by adding context, such as whether a patient is inpatient, outpatient, stable on room air, or needs follow-up. In programming, these labels help organize healthcare information in a meaningful way without replacing clinical judgment. This structure supports clearer modeling of medical scenarios and prepares data for conditions, comparisons, and larger data sets. Python code, clinical status. Clinical status variables describe a patient's current state. Text labels identify care situations, while Boolean values record simple yes or no information. The content defines three text-based patient status fields. The patient is marked as an inpatient, their triage status is awaiting review, and their lab status is pending. Together, these labels summarize key parts of the patient's current clinical situation. The code uses two Boolean flags to track a patient's clinical status. One flag shows the patient is currently admitted, while the other shows that no follow-up is needed right now. The code checks that the patient label is stored as text and that the admission status is stored as a Boolean value. These type checks help confirm the data is in the expected format before it is used for further processing or display. A Boolean value can be converted into text so it can be displayed where a string is needed. In this case, a true or false admission status becomes a readable text value for use in interfaces or reports. The code prints a short overview of a patient's clinical status, including their care setting, triage stage, lab status, admission status, and whether follow-up is needed. It also shows the data types for the patient label and admission flag, then converts the admission flag to text, so the Boolean value is easier to display. This script creates a brief clinical status report for a patient using text labels and true or false flags. It records the patient's care status, pending review and lab results, whether the patient is admitted, and whether follow-up is needed. It also checks the data types and converts the admission flag into text before printing a concise summary of the patient's status and related variable types. Core data types. Integer measurements. In clinical and health data, integers are used for exact whole number values, such as age in years, medication counts, heart rates, steps, or clinic visits. In Python, they represent counts or measurements without fractions. Using integers when values must be whole numbers keeps the data simple, precise, and easier to compare or calculate with. Integers are common in medical settings because many clinical observations are recorded as whole numbers, such as respiratory rates, pain scores, acuity levels, or bed counts. These values support clear clinical communication and reporting. In Python, they are treated as numeric data, so they can be used in arithmetic without being confused with text labels. Decide whether a value should be an integer based on what it represents, not just how it looks. Integers are appropriate when decimals are unnecessary, such as age, measured in whole years or days. But whole-looking values like medical record numbers may be labels, not numbers for calculation. Making this distinction helps prevent errors in clinical data handling. Python code. Integer measurements. Integers represent whole number clinical measurements, while data types help distinguish numeric quantities from labels. Conversions make it possible to perform simple medical calculations accurately. The clinical data stores whole number values for key patient measures: age 42, heart rate 78 beats per minute, 3 prior admissions, and a pain score of 7. Because these measurements are integers, they can be used easily for calculations and comparisons in medical data processing. Numeric-looking values can be stored as text when they are labels rather than quantities. A medical record number may look like a number, but it should remain text because it identifies a record and is not used for calculations. A room label can also be stored as text, especially when it includes both numbers and letters for identification. The code checks the data types of key patient information. It confirms that both age and heart rate are stored as integers, while the medical record number is stored as text. This matters because the record number should function as an identifier, not as a numeric quantity. The total number of patient encounters is found by adding the current visit to the prior admissions count. This updated total is then displayed, showing how integer arithmetic can track and update clinical data. A number stored as text must be converted before it can be used in calculations. In this example, the text value 1200 is converted to an integer, making it possible to add 300 and print the computed result. First, the medical record number is printed as a text label so its format stays intact. Then the pain score is checked with an isinstance function to confirm it is stored as an integer, which supports later calculations or comparisons. This script shows how to use the right data types for clinical information. Numeric measurements such as age, heart rate, prior admissions, pain score, and step counts are treated as integers so they can be checked and used in calculations. Identifiers such as medical record numbers and room labels are kept as strings so they remain unchanged. The script also demonstrates converting a step count from text to an integer before adding to it, highlighting basic type checking, conversion, and arithmetic in a clinical context. Floating point values. In Python, floating point values represent numbers with decimals, making them important for precise measurements such as temperature, weight, body mass index, and medication doses. They are used for continuous data where fractional values matter, unlike whole number counts such as visit totals. Any number written with a decimal is treated as a float, supporting accurate calculations and comparisons in clinical data analysis. Floating point numbers can represent very small or very large values by shifting the decimal point as needed. Because computers store them in binary, they are often approximate, which can cause small differences in calculations or displayed decimals. Health data professionals must decide when to round, preserve precision, or require exact values based on the purpose of the data. Use floating point values for measurements and calculations where decimals matter, such as glucose levels or heart rate variability. Do not use them for labels or identifiers like medical record numbers, which should be strings, or for simple true or false information like admission status. Storing numeric measurements as floats lets Python calculate averages, check clinical thresholds, and convert units accurately. Python code. Floating point values. Floats are used to store decimal medical measurements. This example shows how to compare measurement values and check their types by running each line and reading the output. Several medical measurements are stored as floating point values to preserve precision. These include body temperature at 37.6 degrees Celsius, potassium level at 4.2 millimoles per liter, newborn weight at 3.18 kilograms, and height at 68.5 inches. The code checks that the temperature and potassium measurements are stored as floating point numbers. It uses the type function and prints the result, helping confirm the data has the precision needed for reliable medical calculations and comparisons. The Celsius temperature is compared with 37.5 to check for a low-grade fever. The result is stored and then printed in a message showing whether the condition is met. Convert height from inches to meters by multiplying the inch value by 0.0254. Then present the result rounded to 2 decimal places, giving a clear metric height suitable for scientific use. Body mass index for a newborn is found by dividing the weight in kilograms by the height in meters squared. Floating point arithmetic keeps the calculation precise, and the final BMI is rounded to 2 decimal places for clear display. A temperature reading stored as text is converted into a floating point number using Python's float function. This makes the value usable for calculations and comparisons. Printing the converted value's type confirms that the conversion worked and the data is ready for further processing. This script shows how floating point numbers are used to process medical measurements such as temperature, potassium level, height, and body mass index. It checks that values are stored as floats, uses them in comparisons and calculations, and rounds results for easier reading. It also converts a temperature value from text into a float, demonstrating common type conversion in medical data handling. String data. In Python, strings represent text rather than numbers used for calculation. In healthcare, this can include patient names, medical record numbers, room numbers, postal codes, or status terms like stable and discharged. Even when text contains digits, it may still be a string if it functions as an identifier. Recognizing strings matters because Python uses data types to determine valid operations and helps prevent misinterpretation in clinical data. String data preserves the exact form of clinical and administrative information, including letters, numbers, punctuation, and leading zeros. This is important for items such as lab labels, medication instructions, patient identifiers, and short category values like gender or status. Treating these values as strings helps prevent confusion and supports accurate communication across clinical systems. String data must be consistent because Python treats even small differences, such as extra spaces or capitalization, as different text. This matters when organizing patient lists or matching records, where accuracy is essential. Clear entry rules and careful checking help reduce errors, while strings provide the names, categories, and descriptions that give healthcare data important context. Python code, string data. This example introduces clinical string values. Strings are used to store text labels and identifiers, and Python keeps their characters exactly as written. Patient details such as the name, medical record number, and clinic location should be stored as strings. Even if the medical record number looks numeric, treating it as text preserves leading zeros or other important characters. Using strings keeps the information in its exact format and makes it easy to display or handle later. This example shows how strings can store clinical information. One string records a patient's triage status as urgent. Another identifies a lab specimen, and a third notes a penicillin rash allergy. Together, these values represent categorical or descriptive data used in a healthcare setting. We first display the medical record number to check its stored value. Then we use the type function and its name attribute to confirm that the value is a string. This is important because identifiers may look like numbers but are often stored and handled as text. A text value can store a room number with leading zeros, but converting it to an integer changes how it is represented. The original text keeps the leading zeros when printed, while the integer version drops them. This shows that numeric-looking values should remain text if their leading zeros are important. Create a readable visit label by joining the patient's name with their triage status, separated by a vertical bar with spaces around it. Printing this combined text gives a quick, easy-to-read summary of who the patient is and their current status. This example shows that string comparisons require an exact match. Two text values that look similar can still be unequal if one has different capitalization or extra spaces. When compared, they do not match because the equality check treats those differences as significant. Before comparing two text values, clean one of them by removing extra spaces at the beginning or end and converting it to lowercase. This standardizes the text, so differences in spacing or capitalization do not affect the equality check. This is especially useful when working with user input or data from different sources. This script shows how Python handles strings in a clinical data setting. It demonstrates that patient identifiers and clinical details are stored exactly as text, while converting a room number from a text to a number can remove leading zeros. It also shows how strings can be combined into readable labels, and how differences in spacing or capitalization can affect comparisons. Cleaning and normalizing text helps make those comparisons accurate. Useful built-in functions. Inspect value types. In medical calculations with Python, it is important to confirm how each value is interpreted. Temperatures, pulse rates, and clinical status values may be treated as decimals, integers, or true or false values. Using Python's built-in type checking helps ensure data is stored in a form that can be calculated correctly, which is especially important in healthcare, where text stored as a number can cause errors. Patient form entries such as age, weight, and fasting status may look straightforward, but Python treats each one according to its data type. Text must be converted to numbers before it can be used in calculations, while a Boolean value can clearly represent whether a patient is fasting. Checking data types helps prevent errors when mixing numbers, labels, and true or false values. Checking data types is important when calculations produce unexpected results or when data comes from different sources. Values from spreadsheets, web forms, or questionnaires may not be in the format needed for arithmetic or comparison. Inspecting types before converting data or calculating helps reveal whether a problem comes from the data itself or from the operation. This leads to safer, clearer programs, especially in clinical settings where accuracy is essential. Python code. Inspect value types. Before doing calculations with medical data, first inspect the values to understand what they contain. Python types help guide safe operations, and small records make examples easier to follow. This example stores basic patient form data using appropriate data types: an integer for age, a string for weight that can be converted later, a string for the patient ID to keep leading zeros, and a Boolean value to show whether the patient is fasting. These stored values can then be inspected and used correctly in later operations. We check the data types of key patient fields to confirm they are suitable for later use. Age should be an integer for arithmetic. Weight stored as text would need conversion before calculations. The patient ID is a string for identification, and fasting status is a Boolean for logical conditions. The code first converts the weight from text into a floating point number so it can be used in calculations. It then converts the weight from kilograms to pounds by multiplying by 2.20462, making the value ready for work that requires pounds. The program verifies that the weight input was successfully converted to a floating point number, then displays the equivalent weight in pounds rounded to one decimal place. It also checks that the fasting status remains a Boolean, so it can be used correctly in later logical operations.
The script checks key medical data types before using them in calculations. It confirms that age is stored as a whole number, weight and patient ID as text, and fasting status as a true or false value. It then converts the weight text into a decimal number, calculates the weight in pounds, rounds the result to one decimal place, and verifies the converted type. This helps prevent errors by ensuring medical data is in the right form before processing. Rounding results. Rounding makes numerical results easier to read and communicate.
especially in medical calculations, where extra decimal places can be distracting. In Python, the built-in rounding function lets you choose an appropriate level of precision for results, from division, unit conversions, or dosage estimates. For example, a body mass index may be rounded to 1 decimal place, so it is clearer and more practical to use. Rounding should be done deliberately, especially in clinical and scientific work where small differences can matter. Keep full precision during calculations, and round only the final result when presenting it for readability. This avoids errors from rounding too early, while still making reports and displays clear. Rounding makes datasets and clinical calculations easier to understand by presenting numbers in a consistent way. Using the same rounding approach reduces confusion and helps people compare results accurately. It also balances clarity with the level of precision needed for effective communication. Python code. Rounding results. Rounding helps make clinical numbers easier to read, but precise values should be kept until final communication. Built-in functions can also support simple medical calculations. First, record the raw weight and height measurements, 72.4 kilograms and 1.68 meters. These precise values are used for later calculations, such as body mass index, before any rounding is done for display. Body mass index, or BMI, is calculated by dividing weight in kilograms by height in meters squared. The precise result is then rounded to 1 decimal place, making it easier to read and communicate in clinical settings. To convert 100.4 degrees Fahrenheit to Celsius, subtract 32, then multiply by 5 and divide by 9. This gives the precise Celsius equivalent of the temperature. The Celsius temperature is rounded to 1 decimal place to make it easier to read while keeping enough precision for practical use. This is done with the round function. A height of 66.25 inches is converted to centimeters by multiplying by 2.54. The precise result is then rounded to 2 decimal places, making it easier to read and communicate. The code displays several calculated values in a readable form. It first shows the full precision body mass index, then a version rounded to 1 decimal place. It also prints the temperature rounded to 1 decimal place and the height in centimeters rounded to 2 decimal places. This script shows how rounding makes medical calculation results easier to read while keeping the underlying values precise. It calculates body mass index, converts temperature from Fahrenheit to Celsius, and converts height from inches to centimeters, then rounds the displayed results to appropriate decimal places. The key idea is to present clear, readable outputs without sacrificing accuracy in the internal calculations. Length function. The length function reports how many items are in a collection or how many characters are in text. In medical data, it can help check counts such as patient IDs, temperature entries, or the length of status labels. This makes it useful for verifying data entry and confirming that data is ready for calculations or reports. The length function counts every character in text, including spaces and punctuation. In healthcare data, this helps verify that patient codes and clinical labels have the expected length. Codes that are too short or too long, or labels with extra spaces, can cause matching, sorting, and comparison errors. Checking text length is a simple way to find inconsistencies before they affect analysis. In clinical workflows, the length function helps check how many items are in a collection, such as measurements or patient labels. This count is important before calculating averages or summaries because it affects how reliable the results are. If the collection is empty, it may signal missing data. Checking length is therefore a simple first step for validating data before it supports clinical decisions. Python code, length function. Learn how to use the length function to check the size of data in small medical examples. These counts help support safer clinical calculations. This example stores basic patient data using common data types. A string holds a unique patient code. Another string records the patient's current status. And a list of floating point numbers stores temperature readings for monitoring changes over time. Use the length function to measure key data sizes, the number of characters in the patient code, the number of characters in the status label, and the number of temperature readings. These counts help manage text data consistently and support later calculations, such as finding an average temperature. Before calculating the average temperature, first confirm that at least one reading is available. If readings exist, add them together and divide by the number of readings to find the mean. If there are no readings, the average is set to none because no calculation can be made. The program prints a brief summary of the data by showing the patient code, the length of that code, the length of the status label, and the number of temperature readings. Together, these outputs help learners quickly understand the structure and size of the information being handled. The program prints the average temperature in Celsius and uses the round function to show it to one decimal place. This makes the output cleaner and easier for the user to read. This script uses the length function to measure data sizes in a medical dataset. It counts the characters in a patient code and status label, and counts the temperature readings. When readings are available, it calculates their average and prints the key results, including the rounded average. Checking that data exists before calculating helps handle clinical information safely. In this lecture, you learn to create variables that store medical measurements, patient labels, and clinical status values. Distinguish Python built-in data types used for numeric, text, and true or false medical information. And use built-in functions to inspect and convert values in simple medical calculations. In the next lecture, Lecture C, we will go over control flow basics. Thank you for your attention. See you all in the next lecture.